Here's what everyone gets wrong about AI robots. You hear the marketing pitch from robotics labs. They tell you their AI systems learn from perfect simulated data generated by other AIs. That's the glossy version. But the dirty truth is this: even the most advanced robotics labs in the world still need massive amounts of real human-labeled training data. Unglamorous work, manually collecting footage of robots grasping objects, manipulating items, navigating complex spaces, responding to thousands of tiny human corrections. This is work that absolutely cannot be automated away. It's tedious, repetitive, sometimes physically demanding, and completely essential for building robots that actually work. And now labs are so desperate for this data that they are paying companies like XDOF serious money to handle the grunt work. This isn't the headline-grabbing AI innovation everyone obsesses over. It's the hidden, unglamorous bottleneck holding robotics back. While the world focuses on language model breakthroughs and image generators, the robotics industry is quietly outsourcing one of its most foundational challenges. And here's where it gets interesting. So why can't robots just learn from simulated data? It sounds simple in theory. A researcher writes code that simulates a robot arm in a virtual environment, teaches it to grasp objects in that digital world. Clean, controlled, perfect. But when that robot tries to grasp a real object in the real world, something breaks. The virtual robot's movements don't quite transfer. Real-world friction, material properties, unexpected sensor noise, unpredictable object shapes, all the complexity no simulation can fully capture. Roboticists call this the sim-to-real gap, and it's one of the biggest problems in the field. Think of it like training a pilot in a flight simulator. The simulator is essential, absolutely, but eventually you put that pilot in an actual plane. There will be situations the simulator never prepared them for. Real robots in real environments are chaotic. They encounter objects they've never seen before, textures their sensors haven't encountered, lighting conditions that throw off their vision systems. Researchers realized they needed something different: actual footage of robots interacting with actual objects. Messy, uncontrolled, real-world data. And that's what companies like XDOF are now collecting on an industrial scale. Let's talk about what this work actually looks like on the ground. Imagine a data collector sitting in front of a robot arm, and their job is to manipulate objects, picking them up, placing them down, rotating them, flipping them, while high-speed cameras record every movement and sensor reading. They do this hundreds of times, sometimes thousands, with slight variations each time. Different grips, different objects, different starting positions. The data gets labeled. This is a successful grasp. This is a failure. This is the force applied. All that labeled data feeds into the training pipeline. It's the opposite of glamorous. It's repetitive, sometimes physically taxing, but it's real, unfiltered, unglamorous training data, exactly what robots need to learn from. And scale matters enormously here. A cutting-edge robotics lab might need hundreds of thousands of labeled examples to train a single grasping system. Some estimate millions of individual interactions. XDOF and companies like it realized this was a massive business opportunity. They've built workflows, recruited data collectors, set up infrastructure to handle this work at scale. They are basically the unsung backend of modern robotics development. And this approach is already spreading across the entire industry. So what specific skills are robots actually learning from all this collected data? First, grasping, the ability to pick up an object without dropping it, whether it's a delicate egg or a heavy tool, understanding the object's shape, weight distribution, and texture. Second, manipulation, moving an object to a specific location or orientation. That sounds simple, but involves predicting physics, understanding forces, adapting to unexpected resistance. Third, scene understanding. A robot needs to look at a cluttered tabletop, identify individual objects, understand which ones are graspable, and plan a sequence of movements. That's perception plus planning combined. Fourth, navigation. A robot moving through a real environment needs to understand obstacles, stairs, uneven surfaces, and respond to people and pets moving unpredictably. Each of these skills requires thousands of labeled examples. A team at XDOF might spend weeks collecting data for a single skill, but the payoff is real. Once a robot has seen enough examples of grasping in controlled data collection, it can generalize to novel objects it's never encountered before. The training data teaches the robot's AI system the underlying patterns. That's why this unglamorous work is absolutely critical to robotics progress. But here's what most coverage gets wrong. Now, how does robot training data compare to training language models like GPT or Claude? Language model training works completely differently. Engineers download billions of words from the internet, public text, books, articles, code repositories. That data already exists. They don't need to pay teams to manually collect it. They just download and process it. But robot training data doesn't exist on the internet. You can't scrape a billion examples of robot grasping from the web. There's no robot behavior dataset you can just download and train on. Every robot company needs custom, purpose-built data for their specific hardware, their specific gripper, their specific application. It's expensive. It requires human time. It's not scalable the same way text scraping is. Language models benefit from network effects. Once billions of words are collected, any company trains on them. But robots face a different problem. Each company might need to commission their own data collection or partner with XDOF. This creates a labor bottleneck that doesn't exist in language model training. It's a fundamentally different scaling challenge, and that's why companies like XDOF are suddenly so valuable. The capital required to get robots to human-level dexterity isn't just GPUs. It's also the human cost of data collection. And that changes the entire economics of robotics. So what does this reveal about robotics' future? First, the timeline. If robots need millions of labeled examples to master a skill, and data collection teams can only produce so much data per year, then robotics progress is limited by human data capacity, not just compute. You can't accelerate this just by buying more GPUs. You need more data collectors. That's a labor constraint, not a hardware constraint. Second, the economics. Building a world-class robotics company now requires capital not just for research and manufacturing, but for data collection infrastructure. A startup can't just hire brilliant engineers. They need to fund extensive data collection campaigns. That favors well-funded labs. Third, the human factor. Thousands of people around the world will be employed doing this unglamorous work, manipulating objects for cameras, labeling sensor data, iterating on collection protocols. It's a form of AI-era labor that's often invisible but absolutely essential. Finally, this reveals a hidden dependency in AI development. We talk about transformer architectures, scaling laws, and frontier models. But underneath it all is a foundation of human-labeled data, real people doing real work. This is the truth behind the technology headlines that capture headlines. So how is XDOF actually solving this at scale? Their approach combines several key pieces. First, infrastructure. They've built specialized facilities with robotic arms, sensor rigs, high-speed cameras, and software systems to coordinate data collection across multiple sites. Second, standardized workflow. They've developed detailed protocols for how data collectors manipulate objects, what angles cameras capture, and how to label results. This consistency means quality scales reliably. Third, human capital. They've recruited and trained teams of data collectors who understand the precision required and can execute protocols reliably. Fourth, smart software. They've built systems to assist with labeling, humans verify, but software handles repetitive annotation. This combination lets XDOF handle massive contracts that individual labs couldn't manage alone. They're essentially building the data supply chain for the robotics industry, and it's working. Labs that previously hired their own data collection teams can now outsource to XDOF and focus on research. It's similar to how cloud computing outsourced infrastructure. XDOF is outsourcing the data foundation. The robotics industry is becoming specialized and modular, with companies like XDOF handling the unglamorous foundational work. This model is spreading. Here's what this really means. The flashy part of AI, language models, image generators, frontier research gets all the attention. But underneath every major AI capability is unglamorous infrastructure. For robotics, that's human-labeled training data. Companies like XDOF exist because someone realized this work was too important and too labor-intensive to ignore. It's a reminder that AI progress isn't just brilliant researchers and cutting-edge GPUs. It's also real people doing repetitive, essential work. It's infrastructure and specialized companies handling crucial groundwork. Understanding this changes how you think about robotics timelines. If progress is bottlenecked by data collection capacity, then speed depends partly on how many people do this work and how efficiently companies organize them. That's a different constraint than pure compute. Well-funded robotics companies have an advantage, not just buying chips, but affording extensive data collection infrastructure. The next wave of AI development will depend as much on unglamorous supply chain work as on neural architecture innovation. The next time you see a video of a robot doing something impressive, remember, behind every smooth robotic motion is probably a team of data collectors who spent weeks manipulating objects for cameras. That's the real story nobody talks about. Follow for daily AI news covering the hidden side of AI development.